My name is Matt Hamann, and I'm a co-founder and CTO here at Round. And Rachel just set the stage for what we're going to talk about. Now let's dig in a little bit into what's happening under the hood. So we're going to show you a drone platform that you can essentially build with $300 in compute. So it starts out with our Raspberry Pi. We're using Raspberry Pi 5 to do this. And this thing is really the brains of the operation. We're going to talk more about that here in a second. Not including, this doesn't include the drone. It really just includes the compute. Next, we're using a Halo 10H AI hat. And this is going to help us mostly with vision. We can use it for some inference as well. But in large part, it's really geared toward the vision component of what can the drone see around it. Of course, in order to get things into that pipeline, we need a camera, so we're using the Pi Module 3. And then all this is stacked on top of a drone that's running the PX4 autopilot software. And when we say autopilot, it's not necessarily doing all the decision making for you, because that's really where our Raspberry Pi platform comes in. It's really the piece that helps us tie everything together, that pulls in all the telemetry, and that really enables the compute to talk to the real world and understand what's going on. So we're actually going to run LLM or even small language model inference on a CPU. And it's actually going to be really fast. We're going to see why in a second. But it's the hint there is that our models are actually pretty small. And then we'll control all this with the drone platform using a protocol called Mavlink. So it's one drone, but we're packaging in 3 kinds of intelligence here. And we kind of broke this down into things that maybe tie back into the real world. So you've got the brain, you've got the control system that is understanding the data coming in and issuing commands to the actual drone platform. You've got the eyes, which is, of course, the vision. It's got all the cameras. It's detecting things and feeding that back into the rest of the system. And then you've got the gut, right? You've got those instincts that help you understand what dangers there might be. Oh, I'm about to hit that tree, or I'm going to run into a building, or things like that are really the safety net to make sure that the drone is doing what we want it to be doing at all times. It's the monitoring piece. So let's talk briefly about the brain. It's the part of the drone that listens to your instructions and it figures out, what do I do, right? So let's just take a scenario, for example. Imagine you're a cattle rancher. I know we've got tons of cattle ranches here in North Carolina. Maybe think more Midwestern, right? You've got sprawling acres of land. You've got cows grazing, and you want to say, scan the north pasture. Well, that's intuitive to you, or it's intuitive to one of your farm hands. You say, hey, go check out the north pasture, make sure everything's okay out there. But when it comes down to a drone, if you're having an AI drone do this for you, it doesn't speak English. It speaks this thing called Mavlink, the protocol that issues commands and exchanges telemetry with the drone itself. So somebody has to translate. Now, traditionally, that translator is a trained pilot. So maybe you're using drones, but you're using a human that's going to fly it. And you can just say, yeah, go out and check out the north pasture. They can fly the drone over there, check it out, make sure everything is good, bring it back. What we've done is we've replaced that pilot with a language model. But this is kind of hard, because if you know anything about language models, you know that they are non-deterministic, and you never know exactly what's going to happen when you feed in a prompt and get something back out, right? So this is not just text generation in this case. It's really structured action. And so the model needs to output a function call, or we could say a tool call, with real coordinates and real parameters, and those things have real consequences. If you get it wrong, then you've got potentially like a 5-pound or even heavier aircraft that does something unexpected. And it could be that the consequences are fairly low, right? It just goes the wrong way, or it gets tangled up in a tree or something. But depending on where you're flying these workloads, the consequences could be serious, right? If the computer decides to just stop the rotors midair and the drone falls out of the sky, well, you probably need a new drone, and it could be expensive. But it could fall on someone and hurt them, and that would be a very serious consequence. So we have to be confident that the commands that we're getting out of this model are accurate and exactly what we were expecting. But the thing is we don't need a giant model to achieve this, right? We just need the right small model. We're not running ChatGPT on a drone, right? We're not going to give ChatGPT or Gemini instructions and go back to the cloud. It's going to be way too slow, and it just has way too much knowledge. We don't need all of that. So we're actually going to use a 2 billion parameter model from the Gemma library of models that's been fine-tuned to do exactly one thing, and that is turn natural language into drone commands. So think about it as hiring like a specialist versus a generalist, right? ChatGPT is the generalist. It does things really well. It can read your emails, write poetry, stuff like that. The tuning of Gemma 2 billion is the specialist. It knows drones. It only knows drones. And so it's really good at translating things like, fly to the north pasture into, drone, go to these coordinates and do this thing, or orbit this specific object. And we can define waypoints in the system that give it some clues as to like where to go geographically. But how do we actually get to this fine-tuned model? We're going to use a pipeline that looks maybe something like this. So we need some training data, right, in order to figure out exactly to train the model as to this means this. So we need a bunch of that data that has examples of if I say fly here or orbit this or land or return to home, how does that actually translate into a command that the drone will understand? To do that, we take this training data, we feed it into a fine-tuning platform. So in this case, we're using Llama Farm, which is a completely open source platform for doing inference. It can do vision, and it can also do fine-tuning, which is how we're using it in this case. And it's going to handle the actual training. So it's going to take multiple iterations of this data coming in until we get from, say, 50% accuracy up to 80% and then 90% and so on and so forth. And at the other end, we get our Gemma 2 billion fine-tuned model. We're ready to load that on the drone, and then this could be an entirely separate talk, but we can run it through an agentic router that can understand when we need to call a very specialized fine-tuning model versus something maybe a little bit more generic, still customized to drones, but something with a little bit more reasoning capability, and that's where our OpenHoof agentic routing library could come into play. So you essentially can get a deployable model that does this stuff really well in hours. So now I'm going to have Bobby come up here, and he's going to talk to you a bit about vision on the drone.
Hey guys, I'm Bobby, software engineer here at Round. I guess now formerly a full-time Claude coder at this point. And I'm talking about vision, which I think is the coolest part of it. So we've got the brains behind this. We have a plan for being able to do some navigation. We even have a lot of data coming off of the flight controller, like we know, is the thing moving in a particular direction? How fast is it moving? What's the altitude? There's all this data. It's super cool. But the world is not just those pieces of data for us. I mean, we all have eyes and we see the world, and it has to behave the same way for an autonomous system, in this case, the drone. So how can we do that? And like, what does it actually need to be able to do? So it needs to be able to detect things in the world. So the first point there is detection. So do we see particular objects like cows in a pasture, or maybe a gate in the pasture that is left open? And I'm going to show some recordings earlier of like cars and people. So it can be a lot of stuff. We also need to be able from frame to frame to track an object. So, the cow was moving in a certain direction, the car was traveling in a certain direction, so we can keep track of that. And then the final point there about targeting is maybe you're looking for a very specific thing, a very specific a gate or a car that fits a description, for instance. And the tricky thing about doing this all on a Raspberry Pi is the hardware. Like, it's very limited, and the AI hat is pretty cool. We can get 40 tops out of it, so you can do a decent amount of inference on the edge, on an edge device like this, but you still have a lot of constraints. Like, everything that's going through the system takes away a certain amount of frames per second, and we're trying to get the maximum throughput through the system that we can. And then finally taking all of that and spitting it out in a way that the rest of the drone platform can actually perform actions. So I'm going to walk through what we built as far as the vision pipeline goes. And over there, this is just a recording that came off of the Pi, and you can see little bounding boxes around stuff. And the cool thing about all of this vision AI is it's been around for a long time, and I'm just learning it recently, working with Claude, doing vibe coding, if you will. But so there's some models out there. Most popular is something called YOLO, and there's different sizes and versions of it. The one that we ended up landing on is the small variant, which is the second smallest one. There's a nano. And doing a bunch of benchmarking up front to figure out like what can we run and what's the frames per second we can get, how accurate is it, and truthfully, from a drone's perspective, these models are not great just out of the box because they're not trained at the orientation that a drone might be experiencing the world or perceiving the world. So eventually, I think we're going to move into a model that is more fine-tuned in that orientation. But for now, we're sticking with the base YOLO 11 small variant. And then the second part of this is being able to track. And this is cool because it's all just math. And there's libraries that you can pull in that do all of this for you. We set it on something called ByteTrack, which is just an algorithm that runs. And this is super important because the detection might kind of come in and out. So you might detect something in one frame, but then, for whatever reason, maybe the camera orientation changes or the lighting is slightly different. It doesn't get detected at the same confidence level. So being able to see an object from this frame and guessing or approximating that it was moving in a particular direction, so we're expecting to see it again at a subsequent direction, is what this phase is all about. And again, it's all just math. This is not AI. But this next step is a re-identification phase. So all of the detections in this phase get cropped. So we'll say, okay, there's a car. We see a car. We're going to crop it in that frame, and we're actually going to run it through something called CLIP, which is it's a neural network that basically correlates text and images together. So we can take that cropped image, throw it through this neural network, and then get vector embeddings out the other end. We can store those, and then we can compare frame to frame to, with a much higher degree of confidence, say that this is the exact same car that we saw 30 frames ago in the current frame. And the other reason that this is really important for us is because of targeting. So this is kind of a naive approach at the moment, and it's going to evolve going forward. But someone might be really interested not just in a car, but a silver sedan, for instance. Sorry about the video not loading. There were some issues a few minutes ago. But anyway, you can imagine that you might be interested in a very specific car rather than just a general car, or maybe a very specific gate that is open, not just a gate, because you don't want your cows in the pasture to get out, for instance. So what we can do is compare all of those embedded cropped images that were from the detections against a phrase, or in the future, maybe a set of images that you have that map to the thing. And in that way, you can pass this to the rest of the drone in a way that it can orient the camera in such a way like, I want to follow this thing, or I want to center the image on that particular thing. And then next, the last phase of this is called spatial. So this is, again, this is just a math phase where we take sensor data from the drone, we take camera orientation, and then things like GPS even, and we're able to, with math, say that this bounding box that we detected is at a specific distance from us in meters, at a certain heading from the drone, and this is just data that we need downstream in the final phase, where we then package this all up and we send it through our communication system in the drone, which is just like a pub sub messaging type of queue, so that downstream consumers of this are able to act upon it, like go follow the cow, or orbit something. So that's the vision pipeline as it stands today. And next up, I believe Rachel is going to talk about the gut.
Right, so Matt told you about the brain, like how this drone understands commands, and Bobby told you about the vision, how the drone can see. And we came up with the gut, which is a silly word, but it's really like that reflexive layer. Like when you put your hand on something hot, you don't sit there and think, this is hot, I'm gonna take my hand off of it. You just take your hand off of it because it's your gut reaction. So that's what this layer of the drone is, and that is made up of a couple different anomaly detection models, the monitoring, like Matt mentioned. It's looking at altitude, speed, battery, temperature, so many different little things of telemetry that are coming from the drone so that it can act immediately if something seems off. So say battery drops suddenly, we don't know why, it can just return to home. It can hover in place, it can land, it can decide what to do and act in an instant. So it's the part of the drone that says, don't run into that tree or avoid this power line. You don't have to train all of these little things because you have given it enough data that it can act on its own in that way. And so this really adds a layer of trust to the whole operation. If you are operating a drone and you know that it's going to avoid that tree and go around that building, you can trust that it will actually be able to complete the instruction that you've given it. So that's the third layer, and now we're going to put it all together for a live demo.
Thanks, Rachel. All right, so live demo time. This is always the scariest part of the talk, right? So let's see if we can get this up here. 2 seconds, hopefully. Okay, there we go. Does it have it? I think it's good. Okay, so let me just set the stage here for a second. So all this is real, and as Rachel said, we really wanted to bring a real drone in here and actually fly it, but for the aforementioned reasons, can't do that. But there are some great simulators that all the commands work, all the physics work, everything works. And so we're going to show you a simulation using the actual hardware. So we have a Raspberry Pi. This one's obviously not plugged in, but there's actually one sitting on my desk right now that's driving this entire thing. And you've got the base Raspberry Pi board. You've got the AI hat on top. We've got a camera right here that currently isn't working, and all that. So this is all real. It all works. And what you're looking at here on the screen is something called ArcUI that we built specifically for this purpose. So this is giving you all the telemetry. It's giving you a map of where things are. We've got a chat and a voice interface here as well that we're going to try to use. We'll see how that goes. What we've predefined a waypoint, and we've defined the Durham Convention Center. So we placed our home point for our drone at the Durham Bulls Athletic Park, which is just a few blocks away. And we're actually going to have the drone take off and fly here. So let's give it a try and see what happens. Let's see, just click. Take off. Okay, so it got our command, which is great. We can see that everything armed. It should be talking to us, but we couldn't get the audio working through the system here. Apologies for that. So if you look up in the top left-hand corner, we can see it's now hovering. The altitude has increased. And so now we can give it another command. Fly to the Durham Convention Center. All right, and it started moving. So what's happening here, of course, is, you got a little bit of the voice, but it's trying to say, flying to Durham Convention Center. There you go. And it stopped for some reason. Live demos, right? So anyway, what's happening is the large language model underneath the covers is taking the transcription of what I said. It's feeding it into the flight control subsystem that's running on the drone and sending it off to the destination. So there it goes. It's heading to the Durham Convention Center. And we can actually define missions, right? And say do this, and then do this, and then do this. Now, of course, it thinks it's only flying at 5 meters, so it's going to hit some buildings along the way and crash horribly, and that's where we need the anomaly detection to understand there's a problem here. Simulation not perfect, but here we go. All right, let's tell it to hold in place. Hold. All right, we'll see what happens. Okay, it's hovering in place. Perfect, we got it. So, now we could give it another instruction like, fly east for 50 meters. And again, like we have to orchestrate every step of this because the drone operates in real time at about 10 hertz. And so we need to tell it kind of continuously, what to do. Otherwise, it's like, I don't know what to do, and it'll default to just coming back to base. So let's kind of wrap it up here. Let's bring it back home. Return to home. Let's see what happens. Is it going to make it? It might be lost forever. All right, well, good try. Appreciate your patience here. So it's going to return back to base probably eventually. We could manually override it and tell it to come back. And again, like this is all talking to a PX4 platform. So it's all doing the issuing the right commands. So if you actually put this on a real drone, it'll do what it says. We've got a little work to do in terms of some of the accuracy and things, but it's come a long way. So I think Rachel's gonna just wrap things up, and then I'll be back for a couple last comments.
Okay, so you just saw a drone flying with voice, and we have a little ways to go. We also have a live stream that we're going to connect up to that Matt kind of mentioned with the camera. But let's take a step back and talk about who this is all really for. And so we did some user research, we talked to some operators, and we learned that the people that really want this technology aren't pilots. They're just search and rescue teams hoping to find a hiker. They're farmers monitoring their crops for disease. They're bridge inspectors that don't want to pay for scaffolding. And they're cattle ranchers, as we mentioned, trying to figure out where all their herds are and gates are open. So these are people that might not have connectivity. They might not have access to a screen. They need a voice-powered way of getting a job done. And so that's the type of person that we're building for. Of course, there are plenty of other use cases as well, but these are, So this leads us into what's next. So on top of making this all perfect, we would like to get into a multi-drone swarm scenario where we can have multiple drones, I know it sounds really intense, multiple drones just operating together, right, on one mission across a mesh network in a way that's fully voice controlled. Of course, there'll be a UI for a little bit. There always needs to be some telemetry coming back, but a way that can be done from a mobile device even. So we're really excited to keep building on this, and we're excited to hear what you have to say. Do you want to keep going?
Yeah. All right, so let's bring it home. Wrap it up here, and we'll be happy to take questions afterwards if you want to come up front. But everything you saw today is built on open source technology. So from the models to the embedded platforms to Llama Farm itself, it's all built on open source. Even YOLO and Clip and things like that. So, the piece that we're focused on, is Llama Farm. That's really the core of this. That's tying everything together. There's actually an edge runtime from Llama Farm running on the drone, processing everything and kind of, being the mediator for all those different pieces. That's available as an open source project. You can go and mess with it, download it, play with it. We'd love you to go out and start and support us or try it out, open issues. We love hearing feedback from the community. And we're just continuing to try to develop this to make it, one of the premier world-class LLM runtimes, vision pipelines, and fine-tuning machines around. So again, the team will be available for questions down front here. Feel free to come by, talk to us. We love chatting with the community, and we really appreciate you coming, and thank you for your time. Have a good one.